Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session of work energy and power, so we discussed about the work energy theorem and we solved some questions related to the work energy theorem, right? So in continuation of this chapter, so today we are going to deal with the lecture number 4, where in lecture number 4, so we'll cover some questions on work energy theorem first, and then so we'll see what is the potential energy and what is the gravitational potential energy and what is the spring potential energy and how do we take care of the sign conventions. So everything we'll discuss. Okay, so as usual guys, I just need your attention for the next 1 hour and avoid all the disturbances around you. And one more thing, at the end of the lecture, it's very important to write your own short notes. Chalo, so with very high positive energy, let's start the today's session. So let's start with the interesting question. See here, first read the question guys. So what's the question says? An object of mass m is tied to a string of length L and a variable force F is applied on it. See here, the force applied is a variable force on it, which brings the string gradually at an angle theta. So here is a string originally, right? So here is a an object of mass m. So now the force is applied on it in this direction. So again the force is changing continuously. So then at the end, so the string gradually comes to an angle theta. So like this. So with the vertical. So find the work done by the force. We have to find the work done by the force. Simple concept. I am going to use the work done by all the forces will be equals to change in kinetic energy. The work done by all the forces will be equals to the change in kinetic energy. Okay, so first, what are all the forces that are acting here? So here is a mass m. So this is a mass m. So I can say the gravitational force acts downward, mg, and so the applied force is towards right, and there is one more force. So they said it's a string of length L, so that in the string there will be tension force. So the tension force will act this side, so that the work done by the gravity plus the work done by the applied force F plus the work done by the tension will be equals to change in kinetic energy. So the string gradually comes to an angle theta. So whenever you see gradually or slowly or pulled up slowly, so these terms indicates the change in kinetic energy is 0. Already we discussed it in the last session, right? So now see here, so the work done by gravity, so initially the object is here, so now it is being raised from here to here. So yes or no? So that means it went till here, yes. So now it is raised by some height. How much height it is raised? So vertically some height h it is raised, yes or no? So the gravitational force is downward, but its displacement is upward, yes or no? The gravitational force is downward, but its movement or its displacement is upward. So shall I say that the work done by the gravity is mg into h, so and the angle between they both is 180 degrees, and then so work done by the force we have to find applied force. So and one more thing, the work done by the tension. See here, the tension force is acting upward and the body's displacement is right side. So body's displacement is right side. So the tension force and the displacement are perpendicular to each other, and when the object moves to this point, so then what happens? So the tension will be this side, the string will come here, so the tension will be this side and the displacement will be this side. So this side tension, this side displacement. So at every point the tension and displacement, they both will be perpendicular to each other. So that's why the work done by the tension I am considering it as 0, right? So therefore this is minus mgh, so is equals to plus work done by the force is equals to 0. So from here the work done by the force is equals to mgh. So check the options. So I could not see the mgh. So now what we should do? So let's do a simple calculation. So we have to write it in terms of the string length L, right? So here this is a fixed end and here is a So this is a fixed end, and then here is a string, and then so a mass of object M, a object of mass M is connected here. So then string gradually raised to this point. So here is a mass M, right? So now see here, so it is raised from here to here. We need this height. So this height is nothing but, so whatever the height from here to here, right? So this angle is theta. If you consider this angle as theta, so observe carefully guys. Here, shall I say this total length from here to here, the total length is L, the string length, and here to here also the string length is L. So what is its component from here to here? From here to here, so in this triangle it is L, it is theta. So from here to here the component will be the L cos theta. L cos theta I can say, yes or no? This is L, so that, so its component, so theta is this side, so it's one of its component will be L cos theta. So now I need the H. So shall I say that the L will be equals to, the total length will be equals to L cos theta plus H. See here, the total length is L cos theta from here to here, and H is from here to here. So we need the H. So H is equals to L minus L cos theta. I am sending it to this side. So then H is equals to L, take it a common. So 1 minus cos theta is a H. This is a H value. So now, so what do we get? What did we get? So the work done by the force is equals to mgh. So now in place of H, I am writing mg into, so this is L into 1 minus cos theta. So this is a work done by the applied force. So this is a work done by the applied force. So what is that option? So mgl into 1 minus cos theta. Option 1 is the correct one guys. Clear the concept? Sure. So let's move further. So the interesting question starting itself. So we don't need another slide here. So let's. So next, let's go for the potential energy. So basically in physics, so the potential energy at a point is not defined. So what is defined are then? The potential difference is defined. So the potential energy is not defined. So it's a change in potential energy is defined. The change is defined always. So that is delta U is defined. So delta U is defined only for the conservative forces. So from now onwards, you should remember the change in potential energy is equals to, so the negative of the work done by conservative forces. So it's a negative of the work done by conservative forces. So this is a change in potential energy. So the change in potential energy is equals to negative of the work done by conservative forces. Remember this statement. So very, very useful. So again I am writing it in the statement also. So the change in potential energy is equals to, it's a negative of work done by conservative force. Negative of work done by conservative forces. Negative of the work done by conservative forces. So now see, let's say if there are only two forces acting. So if there are only two forces acting, two forces acting on object, so that is, one is the conservative force. So one is the conservative force and the other one is a external force. So the other one is a external force. Okay. So and so object is gradually moved. So which means, so there is no work done. So that means there is no change in kinetic energy, no change in kinetic energy. So in that case, so work done by all the forces will be equals to the change in kinetic energy. What are all forces that are acting? So one is the external force, the work done due to the external force, and the other one is a work done due to the conservative force. Let's suppose on the body there are only two forces acting. So one is the external force, the other one is a conservative force. Okay, so then according to the work energy theorem, so the work done by all the forces is equals to change in kinetic energy. Now what I am saying is, if the object is gradually moved, okay, so then the change in kinetic energy will be 0. So then the WE plus WC is equals to 0 from here. So WE is equals to minus WC. WE is equals to minus WC. So from here what we can write? So the change in potential energy formula we wrote negative of the work done by conservative force, or in terms of external force, in terms of work done by the external force, we can write it as, in place of minus WC, shall we write WE? That means the change in potential energy, either you can write it as a negative of the work done by the conservative force, or simply so work done by the external force. Understood, guys? So from now onwards you have to remember these formulas. So this will be useful in further chapters itself, further chapters also. Clear? Understood? Chalo. So let's move further. So let's solve some questions so that you will get the idea how to solve the questions. See here, the potential energy of a body in position A is minus 40 joules. Take care of the sign conventions. A point is there, and work done by a conservative force in moving the body from A to B. So it is moved from A to B. Okay, so chalo. So find the potential energy of the body at position B. So the potential energy at A is minus 40 joules. So we have to find what is the potential energy at B. So the work, which work is done? The work done by the conservative force in moving from A to B. A to B. So we know that the change in potential energy is equals to negative of the work done by conservative force, because they said clearly the conservative force, right? So what is change in potential energy? So final minus initial. So which is UB minus UA is equals to minus of, so what is the work done by the conservative force? So the work done by the conservative force is minus 20 joules. See here, minus of minus 20 joules, right? So UB minus, so what is the work done by, what is the potential energy at point A? So minus 40. This is minus 40. The potential energy at point A is minus 40. So which is equals to 20. So from here, so the UB is equal, UB plus 40 is equals to 20 here. So then the potential energy at B will be equals to, so 20 minus 40, which is minus 20 joules. So the potential energy at B point is minus 20 joules. Option C is the correct one, guys. Understood the concept, everyone? Chal. So let's move further. So now, so we can write this conservative force, the work done by the conservative force, or the change in potential energy in terms of conservative force. So we know that just simple steps, understand carefully here. So the change in potential energy is equals to, so negative of the work done by conservative force. So now if there is very small change in conservative potential energy, if there is small change in potential energy, which is equals to minus, so minus dWc, so very small work done. Yes or no? Work done by the conservative force. So now, so I can write, so the du is equals to, so in place of dWc, so shall I write, so the Fc, the conservative force, into the dr. So the conservative force into dr, right? So this you can write it as, so the du, the change in potential energy, or else the total change in potential energy delta u, if you integrate it on either side, so the change in potential energy delta u, negative of, so integration of x1 to x2 fx dx. Already we have seen this, right? So this part we already know from the previous sessions. And then integration y1 to y2, so fy dy, and then plus the integration z1 to z2, so fz dz. Fz dz. So this is a concept. This is a change in potential energy. Hope the concept is clear, guys. Yes? Chal. So let's solve the question so that you will understand even better. See here, if a conservative force, so this is a conservative force, what is this? Fc is given, so which is 2x I cap plus 3y square j cap. So now, so find the potential energy at 3 comma 4 if the potential energy at 2 comma 1 is 8 joules. So here is the point 2 comma 1 and here is the point 3 comma 4. Okay, so let it be point A, let it be point B. Okay, so initially the potential energy at this point is 8 joules. Okay, so what is the potential energy at B we have to find. So we know that the change in potential energy is equals to, so in terms of force I am writing, so negative of, so the integration of fx dx from x1 to x2 plus integration of y1 to y2, so fy dy, so plus the integration of z1 to z2, so fz dz. So this is a force, right? So chalo, so here there is no z term, so I can ignore this, so this part will be 0. So the change in potential energy is final minus initial. So what is final? ub minus ua is equals to negative of, so integration of, what is x1 to x2, this is x1, this is x2, 2 to 3. So what is the force in the x direction? We have got 2x, so 2x dx plus, so the integration of, so y1 to y2, so 1 to 4, so 1 to 4, so then what is this one? 3y square, so the force in the y direction is 3y square dy. Clear guys? Sure. So let's do step by step so that you will understand easily. Right, done? Sorry. Yes, so now let's go for the next one. So the change in potential energy ub minus ua, which is nothing but, so the potential energy at B minus the potential energy at A is already given 8, which is equals to, so negative of, so here we get, so 2x square by 2, so that is x square, so 2x square by 2 means 2 cancels, x square from where to where? 2 to 3 plus, so this is 3y square, y cube by 3, where 3 gets cancelled, so y cube from where to where? 1 to 4. So now substitute the upper limit and lower limit here. So ub minus 8 is equals to minus of, so this is 3 square 9 minus 4, which is 5 plus, yes or no? So 3 square is 9 minus 2 square is 4, so total 5. So this is 4 cube, which is 64, yes or no? So this is 64, yes, 64 minus 1, so which is 63. So fine. Chalo. So ub minus 8 is equals to minus 68. So send this minus 8 to that side. ub is equals to minus 68 plus 8. So here we get the ub is equals to minus 60 joules. So the total final potential energy at B is minus 60 joules. Option 1 is the correct answer, guys. Clear the concept, everyone? So let's move further. So now, what is the gravitational potential energy? See, as we discussed earlier, so the potential energy at a point is not defined. So it's a change in potential energy that is defined. So generally, what we consider is, so let's suppose there are two masses m1 and m2, so which are initially at infinite distance. So initially they are at infinite distance. So now we are bringing them to certain distance. So that means the distance between them is some r. Initially they are very far away. So now you are bringing them to some distance r. Okay. So now, so this is the initial, the initial potential energy is 0. Whenever in physics we consider the potential energy at infinity is 0, the potential at infinity is 0. Okay. So here the initial potential energy is 0. So what is the final potential energy when you bring them to this point? So G m1 m2 by r. So this is G m1 m2 by r. So therefore the total potential energy, the change in potential energy is equals to U final minus U initial. So U final minus U initial, which is equals to, so U initial is 0. Simply the U final itself is a change in potential energy, which we can simply also write the potential energy at that point. Clear guys? Understood? Sure. So this is we'll learn in detail in gravitation chapter as well. Just remember the formula. So the potential energy between the 2 points, which is G m1 m2 by r. right? So whereas if the point for points close to earth surface, so from the surface from the earth surface, if they are at a height h above, so let's suppose this is a mass m, sorry, so here is a mass m object, so which is h height from the earth surface, so then the potential energy of it will be mgh. So the potential energy will be mgh. Clear? So if there are two objects, let's suppose, so let me take here. So if there are two objects, so consider, so this is the earth surface, so here is a mass m, so which is at a height h1, and then so there is a mass m2, so which is at a height h2. So then so the initial potential energy of this one is, the initial potential energy is mg h1, and final potential energy is mg h2. So then the change in potential energy, which will be equals to final minus initial, right? mg h2 minus mg h1. So from here we can write mg, so take it out, so h2 minus h1, or we can also write the change in potential energy is equals to mg into delta h. So mg into delta h. Clear, guys? Understood the concept? Sure. So now let's take a simple question here. So what's the question says? The work done in raising a 15 gram mass of 15 gram from the ground to a table of 1 meter height. See here. So initially it is on the ground. So see, initially it is on the ground. So this is of mass m. So now it is raised to some height h. So it is raised to some height h. So how much height? So that h is equals to 1 meter, they said. Okay. So then this is of mass 15 grams. So shall I say that here the initial potential energy is 0, because initially it is on the ground. So if it is on the ground, the initial potential energy is 0, or else you can directly write this formula. So which one? So the delta u is equals to mg delta h, which is nothing but so mg into h2 minus h1, right? So here mg, so h1 is 0, right? So this h1 becomes 0 directly. The change in potential energy is mg h2. So what is the mass? It is given 15 grams, converted to kg. So 15 by 1000, g is 10, height is 1 meter. So 10 10 cancel. So 15 by 100 means 0.15 joules. So 0.15 joules. Clear, guys? Understood, everyone? This part? Chalo. So let's go for the next question. A chain of mass m and length l is kept in 3 positions as shown below, assuming h is equals to 0. So the ground on the ground, find the potential energy of chain in all 3 cases. See here. So in the first case, so the chain is kept horizontally on the ground. So that means there is no height, right? So h on the ground, so h is equals to 0. So here what will be the potential energy? So the potential energy will be equals to 0, I can say, in this particular case. Where in the second case, so the chain is raised to some height h. The chain is raised to some height h. So in this case, the potential energy will become mg. So to how much height it is raised? So see, simply it is actually, so the change in potential energy is equals to mg h2 minus h1, right? As h1 is 0, because initially it is on the ground, then it is raised to some height h. So that's why mg h2. So h2 means here simply h, right? Understood? So in the second case, the change in potential energy is mgh. So now let's see in the third case. See, so it is there on the ground and it is there at some height h. So now which height we should consider, sir? So should we take the potential energy is equals to mgh or 0? Because some part is touching the ground and some part is at the height h. In this particular case, what you should do is, so its center of mass is at what distance? So consider where its center of mass lies. So let's suppose this is its center of mass. So if this total height is h, so its center of mass lies at a height of h by 2. So its center of mass lies at a height of h by 2. So therefore the change in potential energy will be equals to, in this case, so mg, so h by 2, so which is nothing but mg h by 2. So completely you can write like this, so mg h by 2. Clear? Understood, guys? Sure. Next, so let's move further. So let's go for the next question. See here, so try to understand the given question. A meter stick of 400 grams is pivoted at one end, so it is pivoted at one end, so and displaced through an angle theta. See here, this is a meter stick, so it is pivoted at this end, so now it is displaced from here to here like this. So the meter stick means its length is 1 meter. See here, so its meter stick means its length is 1 meter. Okay, sure. So now displaced an angle 60 degrees. So the increase in its potential energy is, see here, so the meter stick, so its total length is 1 meter. Its total length is 1 meter initially. So now, so its initial potential energy, what is its initial potential energy? See here, so its initial potential energy Ui, so consider this as the ground. Consider this as the ground. Okay, so now some part is touching the ground and some part is at a height h or 1 meter. So now same this case, some part is touching the ground and some part is at height h. So then where did we, what is the total height we should consider? So wherever its center of mass lies, so that's it height, actual height. Okay, so that's why in this particular case, so its center of mass lies at a distance of h by 2, so which is nothing but half meter, I can say. So its center of mass is half meter, so which is nothing but the initial potential energy. So its mass mg, let's write its mass into m into g into, so at how much height it is? 1 by 2. So therefore, so the initial potential energy is mg by 2. Mg by 2. So now let's write, so the final potential energy, or else let's okay, fine, let's write, so this as mg by okay, fine, let's okay, let it be, here we already got, so this is mg by 2. So now finally, so it has reached this point. See here, so finally it has reached this point. So we are considering this is the ground, so then its center of mass has shifted to this place, yes or no? So it's, see, don't commit the mistake here. So this is already L by 2, which is nothing but half, so initial potential energy. So now what will be its potential energy? So the final potential energy, so it's already from here to here, so if you consider this as length L, so this is going to be the L cos 60, actually it's going to be the L cos 60. But what we should consider here, which length we should consider here? So its center of mass moved to this point, yes or no? So and then, so it's L by 2, the final potential energy is, so mg into, so what is the length there? So the length here it is going to be L by 2 cos 60, L by 2 cos 60 degrees. Understanding why, guys? Because its center of mass has shifted to again half, so that's why its length is going to be half of it into, so cos 60, here L by 2 means, let's write 1 by 2, so 1 by 2 into, so its component, what is its component? So cos 60. Understanding? So this is the initial potential energy, this is the final potential energy. So now let's write the change in potential energy, so which is U final minus U initial. So I can take mg common in both, so final minus initial means this is going to be 1 by 2, so into cos 60 is also 1 by 2, so minus, so that is 1 by 2, so which is nothing but mg into, so 1 by 4 minus 1 by 2, right? So which comes out to be, yes or no? So final minus initial, the change in potential energy, so which is nothing but, so mg into, so the 4 is the LCM, so where we get, so this is 1, this is going to be 2 times, so which is nothing but minus mg by 4, so minus mg, so substitute the values, so which is nothing but minus m, what is mass? 400 grams, so 400 by 1000 into g is 10, into 1 by 4. So here it is 1 0 1 0 cancel, 4 ones are 4 hundreds are, so which is 100 cancel, so which is minus 1 joule, so which is nothing but you can take the magnitudes only given here, so 1 joule. Okay, so basically actually what we have to do is it is raised to some height, right? So this is the height we required. This is the height we required. So you can subtract this minus this. You can subtract this minus this, then you can get the 1 joule. So anyway, it's fine. Understood, guys, this question? So again, I am writing. See here. So this is actually the meter stick. Again, listen. So this is actually the meter stick. So here it is its center of mass. Now it is rotated by an angle 60 degrees, right? So that its center of mass shifted to this place. Its center of mass shifted to this place. So now we need this height. So we need this height, right? So the change in potential energy is mg into delta h, right? So mg into what is delta h here? So this is already this, from here to here it is L by 2. From here to here it is L by 2. So now this side, what is its component that comes here? L by 2 cos 60. This component is L by 2 cos 60. And this whole thing is L by 2. Yes or no? This whole thing is L by 2. So now we actually needed, so the L by 2 minus L by 2 cos 60. So you do this way, it will be easy. Okay, so that we get mg into, so L by 2 minus L by 4. So now you get the same answer, which is 1 joule. In place of L, you substitute 1 joule. So because it's a meter stick. Clear, guys, the concept? Done? Chal. So let's move further. So let's take the question number 7. So what's the question says? Try to understand this question. A uniform chain of length L and mass M is lying on a smooth table, and 1/3 of its length is hanging vertically down over the edge of the table. See here. So let me consider this is a table. So this is a table. So now a chain is kept on this surface. So this is a smooth surface. There is no friction. So this chain has length L and mass M. So that means, so its total length that is hanging 1/3 of its length. See here. So 1/3 of its length is hanging vertically down. So this length is L by 3. Yes. So now, so the total length of it is mass M and length L. Yes. Fine. So now, so what's the question says? If G is the acceleration due to gravity, the work required to pull the hanging part onto the table. So what is the work required to pull the hanging part onto the table? So this whole chain, you have to pull it onto the surface. Okay. So now what I am considering is, let's take this as a reference. So consider this is a ground. Consider this is a ground. Right. So now, so what is the initial potential energy? See here. So the initial potential energy is, so its mass. What is the mass of it? See, L by M mass as the length, sorry, L length has mass M. So then L by 3 part will have, so the mass of M by 3. So that's why, so as it is downward, I am taking its mass is M is M by 3. So downward potential energy. So because below the ground, right? So minus M by 3 into, so G into, so what is the height? What is the height you should consider? See here. So this is the total height which is hanging, but we should consider its center of, some part is touching the ground and some part is at a distance L by 3. So you should consider its center of mass. So its center of mass will be half of its length, which is L by 3 by 2, which is L by 6. So that means its potential energy will be minus mgl by 18. So this is a potential energy. And when you completely pulled it onto the ground, so the final potential energy will become 0. When you completely pulled it onto the ground, so there is no height, right? So it is now completely on the ground. See here. So now it is completely on the ground. So that means, so there is no height. So therefore the potential energy, final potential energy is 0. So therefore they are asking what is the work done. So the work done is equals to change in potential energy. Sorry guys. So the work done is equals to the change in potential energy, which is nothing but U final minus U initial. So what is U final? 0 minus what is U initial? Minus of mgl by 18. So which is nothing but, so this whole thing is mgl by 18. So the correct answer is option 4, mgl by 18. Clear guys? Understood the concept everyone? Sure. So let's move further. So now let's move for the next concept, that is spring potential energy. See, so whenever a spring is at rest or at its natural length, so initially, so here is the spring which is at its natural length, that means so it's not stretched or not compressed, so then in that case it's called the natural length. So when the spring is at its natural length, okay, so its potential energy is 0, we consider. Okay, so if the spring is stretched by some distance x, so then some potential energy will be stored in it. So what is that potential energy? So half kx square. Half kx square is the potential energy stored in the stretched string or the compressed string. So if you compress the string by some distance x, so then in this case also the potential energy stored will be half kx square, and we already seen in the previous chapter. So what is in NLM, so there is a spring force. So the spring force always tries to bring the spring to its original position, right? So our natural length. So if you are applying the force this side, so if you are stretching it this way, so the spring force will act this side, right? So what is the spring force formula? So the spring force is equals to kx, right? Actually it is minus kx, so just I am taking the magnitude. So kx, so it will be always towards its mean position, yes or no? So the spring force is kx. So here k is called the spring constant. So in potential energy formula and in spring force, in both the cases, so the k is the spring constant. The k is called the spring constant. Okay, so what are the units for the spring constants? So what are the units guys? So the spring force means F. So F is equals to kx. So from here k is equals to F by x, which means so its units are Newton per meter. X is a displacement, so its units are Newton per meter. So can you guys write down its dimensional formula as a homework? Write its dimensional formula as a homework. So what is its dimensional formula? So take this as a homework. Clear? Understood the concept? So whenever the string is stretched or compressed by some displacement x, so then the energy stored in the spring is called the spring potential energy. So that spring potential energy is half kx square, where x is the displacement that you stretched or the displacement so that you compressed. Clear? So chalo. So and the spring force will always act towards its original position. So the spring force formula is kx. Okay, so let's solve some questions now to have the better understanding. Let's solve some questions guys. So what's the question says? So the first one, when a long spring is stretched by 2 centimeters, its potential energy is U. So if the spring is stretched by 10 centimeters, so what is its potential energy stored in it? See here. So this is a spring, so which is stretched by 2 centimeters. So let's suppose it is stretched by 2 centimeters upon applying the force. So let's suppose some force is applied. So in this particular case, so the potential energy is U, they are saying. So what is the potential energy formula? Half k x square. So how much distance it is stretched? Half into, so the spring constant is not given in the question, so but the displacement is given, so 2 square, so which is nothing but so half k into 4, alright, 2 square is 4. So from here, so I can write this is 2k, so the U is equals to 2k. So then in the second case, it is stretched by 10 centimeters. So the same string, if the spring is same string, spring means the spring constant is same, k is going to be same. So now let's suppose it is stretched by 10 centimeters. So now let the potential energy in the case to be U2, so which is equals to half k x square. So how much distance? So k, spring constant is same in both the cases because the spring is same, right? So here 10 whole square because it is stretched by 10 centimeters. So I am writing it as k half into k into, so this is 100. So this we can write it as 50k. So 50k, so which I am writing it as 2 into 25k. So 2 into 25k. So which means the potential energy stored in the second spring will be equals to 2 times, so 25, let's write 25 into 2k. Let's write 25 into 2k. So then in place of 2k, I am writing the potential energy stored in the first spring. So that means, so when it is stretched by 10 centimeters, so its potential energy will be 25 times the first one. So it will be 25 times the first one. So in terms of u they said, so that's why I am writing in terms of u itself. So which is 25u. Clear guys? Sure. Let's go for the next question. Same kind of question again. The potential energy of a spring when stretched by 2 centimeters is u. So initially it is stretched by 2 centimeters. So let's write, so it is stretched by 2 centimeters. So potential energy they said u. So half k x square means here 2 square. So which is half k times 4. So which is nothing but 2 times k, right? Chalo. So then the same spring, if it is stretched by 8 centimeters now, so it is stretched by 8 centimeters. So then in that particular case, so the potential energy, let it be u2, so which is half. So the spring is same, so the k will be same. Yes. So into, so what is x here? So 8 whole square. So it will be half into k into, so 8 square is 64, right? So 2 ones are 2, 32 times. So 32k, right? So then, so I am writing it as, so 16 into 2k. So which we can write it as 16u. In place of 2k, I can write, so u. So therefore, the potential energy stored will be equals to 16u. Option 4 is the correct one. Clear guys? Simple questions, right? Chalo. So let's go for the next question. So what's the question says, see here. Two springs A and B having the spring constants Ka, Kb, where the relation between Ka and Kb is Ka is equals to 2Kb. So are stretched by applying the force of equal magnitude. So that means same force is applied. If the energy stored in the spring A is Ea, and then energy stored in the spring B will be, so in terms of Ea we required. So understand, see here clearly. So let's suppose this is a spring A. Okay, so this is a spring A. So some force F is applied on it. Okay, so then let the displacement be XA. We know that, so let this spring has some spring constant K. So F is equals to, we know that K into XA, K into XA. So therefore the displacement in the first spring or in the A spring is, so simply, so F by, so the spring constant Ka. So the first spring constant is Ka. So F by Ka. So therefore, so the potential energy stored in the first spring, so let it be UA I am writing. So let it be UA is equals to half into Ka into XA whole square, right? It should be XA whole square. So which is nothing but half into Ka into, in place of XA whole square, I am writing F by Ka whole square. Yes or no? The displacement is X by F by Ka. So let it be the equation number 1. So now similarly, let's do for the second spring also. So let it be the second spring. So where same force is applied. See here. So whatever the force in the previous case, here also the same force is applied on the spring B. So let it be the spring B, whose spring constant is Kb, and whose displacement is, let it be Xb. So now I know that force is equals to, so the spring constant Kb into the displacement Xb. So right, so from here, so the displacement Xb is equals to F by Kb. The displacement Xb is equals to F by Kb. So from here, so let's write the potential energy stored in the second spring. So Ub is equals to half Kb into, so Xb square, Xb whole square, right? So here I am writing half into, so Kb into, in place of Xb, I am writing F by kb whole square, F by kb whole square. So let it be equation number 2. So now let's divide the equation number 1 by 2. So which is nothing but UA by UB is equals to half. So the first one KA into here F by KA whole square, right? So this is half KB into, so here it is F by KB whole square. So then I can write this as, so half KA, here this one F square by KA square by, so half KB F square by KB square, right? So from here, so let's write half gets cancelled, 1 KB gets cancelled, 1 KA gets cancelled. So F square gets cancelled. We left with 1 by KA by 1 by KB, right? So therefore, so the UA by UB, so is equals to, shall we write, so KB by KA, and in the question they already gave, so the relation between KB and KA, so KA is equals to 2 KB. So in place of KA I am writing 2 KB, right? So therefore KB cancels, so 1 by 2. So that means UA by UB is equals to 1 by 2. So from here the potential energy stored in the second spring is 2 times of potential energy stored in the first spring. So as they said in terms of E, let me write EB is equals to 2 times EA, right? So just in place of U I am writing E. So EB is equals to 2 times EA. So option 1 is the correct answer, guys. Clear? Understood? Chal. So let's move further. So the next question, what's the question says? Two similar springs P and Q have spring constants K and Kp and Kq such that Kp is greater than Kq. So they are stretched by first by the same amount of, they are stretched first by the same amount, then by the same force. Okay. So same amount means, see here. So let's suppose this is a spring P. Let's suppose this is a spring Q. So it is stretched by, let's suppose, some x distance. So it is also stretched by some x distance, right? So then, so what is the work done by the springs WP and WQ are related in case A. So in case A I am finding first. So they are stretched by same amount. So the potential energy stored in the spring P will be equals to half into, so the spring constant Kp into the displacement x square. So the potential energy stored in the second spring will be half into, so the spring constant Kq into, so the displacement is same. If you observe in these both, so half same, x square same. So that means the potential energy in the spring P and spring Q, it's depending on the spring constants Kp and Kq. So they said Kp is greater than Kq. Kp is greater than Kq. So then I can say the potential energy in the first case will be obviously greater than the potential energy in the Q. So because Kp is greater than Kq means this value will come more. So that's why, so potential energy means the work done. So the work done in the P will be greater than the work done in the Q. So this is not, so this is not, this is correct and this is wrong. So directly with the first one you can say the answer, right? So let's solve the second one also. So in the second case, so they by the same force, if they are stretched by the same force, see here, this is a spring P. Okay, so let's suppose it is stretched by some force P. So let's the displacement xp. Okay, so what is the potential energy in the P now? Half into, so Kp into, so the xp whole square. Yes or no? So what is the force is equals to, we know that K into xp. From here xp is equals to F by x, F by K, sorry, F by Kp. Yes or no? So here in place of half Kp into, in place of xp I am writing F by Kp whole square, right? So here 1 Kp cancel, half into Kp, this Kp gets cancelled, F square by Kp. This is the potential energy stored in the P. So if they are applied by the same force, the second case I am talking about, same previous type question, this one, right? So then I am taking the spring Q, right? So where the force applied is same force F. So let the displacement be xq. So therefore the force is equals to xq into kq. So from here the displacement xq is equals to F by kq. So the potential energy in the spring q will be equals to, so I can say half into kq into, so xq whole square. So here half into kq into, so what is xq? F by kq whole square. So here 1 kq gets cancelled, so half into F square by kq. So this is a work done in the q, so which is equals to the potential energy in the q. So this is the potential energy in the q, p, and the work done in the p. Yes. So now if you observe, so the potential here kp is in the denominator, here kq is in the denominator. So they said kp is greater than kq. The kp is greater than kq. So here kp is more, so that means the potential energy will be less. Here kq is less, so that means the potential energy is more. So that's why the work done in the second case will be greater than the work done in the first case. So the same option we are getting. Clear, guys? Hope you guys understood the concept. So that's it for today. So we have seen, so what is the potential energy concept, and so the work energy theorem questions. So in the next session, so we'll meet with the lecture number 5 of the work energy and power. So till then, keep studying. All the very best, guys. Bye.